as a lot of you probably already know, gravity causes things to fall. But what gravity really is, or can be approximated as, is an acceleration on any object. So we are constantly accelerating towards Earth core. And if you're able to drop something higher, you are able to see that every second that goes by, that object will be increasing in velocity by 9.8 meters per second. So if you drop a rock after 1 second, the velocity will be 9.8 meters per second. And if you do the math real quick, you can even see this. All right. Oh my goodness. So 9.8 would be our final velocity minus 0 divided by 1. This is that classic formula of VF minus VI divided by T. And that gives us an answer of 9.8. Oh, you can't see it. 9. Negative 9.8 meters per second squared. The reason it's negative is because we see that we are falling downward. We're going towards the center of the Earth. We define that as negative. Anything that is dropped will be a negative acceleration. So technically, this is negative 9.8 meters per second. Okay? So let's keep moving on. So like I was saying, why is it negative 9.8? Well, let's look at this image real quick. I'm going to take my face off. At 0 seconds, we're at 0 meters. At 1 second, we're at negative 9.8 meters per second. 2 seconds, negative 19.6. It's just decreasing by 9.8 each time. Or if you want to think about it, we're increasing in value, but just going in the negative direction. And by 5 seconds, we're already at negative 49 meters per second. And to double check that these numbers are correct, we can use the formula like I just did. Let's check. Let's do 5 seconds. Let's compare a non-zero. Let's compare this one and this one. Okay? So we have A is equal to our final, which is negative 49. It's the further one, minus a negative, so that would just make this plus 19.6. Okay. Divided by 5 minus 2. So that's actually why we say delta t. So it's final time minus initial time. So A is equal to negative 49 plus 19.6 is negative 29.4 divided by 3. And what do you know? That's equal to negative 9.8 meters per second squared. Remember, acceleration is meters per second squared because we're changing in meters per second every second. That's what an acceleration is. And if you actually do the math here, if we were to compare 3 to 0, we would have the exact same thing as what we did right here. But negative 29.4 divided by 3, oh my goodness, negative 29.4 divided by 3 gives us negative 9.8. Cool. Awesome. Math is pretty neat. So I know I've been saying this is like an approximation and we don't really need to understand gravity, but if you are curious, I will link a video in the YouTube description that actually goes into what gravity actually is. Because gravity is weird and it's a warping of space-time. And it gets all crazy if you think about it that way. So we just kind of simplify it for this class and we're able to say, oh, it's negative 9.8. Right here I say negative 9.81. Ignore the 1. Color that in. Okay. It's negative 9.8 for this class. This is what I used in college. You don't need that for college math because we don't do college math here. So air resistance is an extremely complicated thing that even scientists struggle with. There is an entire field of meteorology that's really just studying the way air flows. in order to determine weather. And if you can see how crazy and different each of these people's faces look, air has a lot of power and the ability to change things pretty rapidly. You can see this guy's barely able to stand against the force of the wind. This kid, it's a classic one. Not really that strong a wind, but he's getting bobbled around. And right here, I think, shows a really good example of why we're ignoring it. Gravity can be overtaken by air resistance if it's strong enough, but also he is able to manipulate how he falls just by changing the way he's shaped. So it's much easier to just completely ignore it and understand that maybe you might be noticing mass and weight don't have anything to do with how fast something falls in a vacuum. Because this guy weighs the same. All he's doing is changing his size. And it's affecting how the air pushes him around. So, with that, let's say you're running off a cliff for whatever reason. You realize there's not water beneath you. Your last possible hope is that somehow we are living in a simulation and you're able to survive the Looney Tunes drop, which is just don't look down. If you look down, you're definitely falling because you realize you should be falling. But this is a last hope. Don't go running off cliffs or anything like that, because for the most part, I don't think I've seen any scenarios where we broke the simulation Matrix style. So yeah, don't jump off the cliff, kids. That's what I wanted to say. Public safety announcement, public service announcement from Stessel to you. Running off cliffs is dumb.